So what I'm going to present is actually about 1/2 of my PhD topic, plus some more technical details and less of the theory. So what was the motivation at the beginning of my PhD? That we were collaborating together with the physics department, and they want to compute basically that formula. This slide doesn't have to really mean something to you. It's just the physics background and meant to impress people. But what's behind is actually that space-time, 4-dimensional space-time, is discretized in all 4 dimensions, 3 space dimension, 1 time dimension. And the most computational intensive part is the stencil operation, which takes it from all of the neighbor points. So in 4 dimensions, to the direction in each dimension makes 8-point stencil out of it. So one part of the time there was that I optimized it manually, writing assembly code and so on, and a lot of the work was managing buffers, transfer communication buffers, data that I want to transfer from this node to this node, have to put it in a specific slice, have to unpack it again, and finally I did so much of it later that I wanted to optimize it. The result then is an extension to LLVM, which I called Molly. So here an example on the right side is part of the manual written code that I started with. It's quite extensive. It's written, optimized for different architectures, and so on. So to explain what I wanted to do, I'll just give a brief explanation into the Polyhedra framework as used, for instance, by Poly. So what we have, basically we start with a loop structure. Here's an example, and we say in this example there are 2 statements, and they're executed, each statement is executed at a specific point of the loop counter variable. And this makes up a domain of the statements. This is basically what Poly does. So my idea was I try to extend it to the arrays as well. I represent them as polyhedra, as them, and then can apply transformations on those polyhedra and can, for instance, distribute them on different nodes just as I want, and this would handle all my buffer problems. For this one, I had some extensions, especially the most important, since we want to transfer data from one node where it's produced data to the node where it's actually required. So it's a generator-consumer relationship, or what's in theoretical terms to be a flow dependencies. The others are actually not that important on it because that's not actually data need to be transferred. It's just the change of the ordering that we have to ensure, which is already taken care of by Poly. What you also have, we need to have a node or something in front of the loop structure. That is, if there's a value not written, not produced in the loop structure, it must have been the value before. So, and the same one for the exit one, when there's a value visible to other code afterwards, it's we can think of the epilogue at the end to have produced it. So virtually we can think of the top node to produce all the values, which are then might be consumed by parts statements within the scope, and produce such that the epilogue node will consume that node. We also have an extension. I make a distinction between fields and variables, where fields are distributed along all the nodes. We have you can see it as a distributed memory architecture, and we distribute different elements of those arrays to different nodes. Whereas for variables, we say it's private per node, so which are not then distributed. So what we have to care for is, or think of, where do we put the nodes, the array elements of the fields. We need to put them somewhere. This is, was actually not the core part of my PhD thesis, my contribution. I applied some relatively simple heuristic on it, which is just block distributions. It's a default one, or it's user supplied. If you want to have more sophisticated things, it's known as, in literature, as the alignment problem, because we might want to if we have one value on one node and we want to have another node, a value on the same node, so aligned to each other because they're used at the same time. What other problem is there? It's a work distribution. That is, where actually want to execute on which processor do we want to execute the work that is to do. This is actually also not really core part of my contributions. So it's somewhat related to alignment. I also applied a simple policy, usually known as owner computes, which usually works quite well in the literature. As alternative, it can also be user supplied. So what's the core part of my thesis is to organize how we organize the data transfers between the nodes. So we have a consumer and a generator, which produces some value, and how do I get this value to the actual consumer without recomputing everything. So for this, I used a notion called chunking. Chunking function actually says what values we want to put together into one message. When the chunking function says value for different value for different inputs, it's basically saying we want to put it in different values, otherwise you put it into the same message. There's a trivial one saying just give me every input which would just put all the values into the same message. So we have to then, when we want to find a chunking function, what do we care for? And the prime optimization goal I chose is we want at the end have a program run with the fewest number of messages possible. So if we have just a non-parametric loop structure, that is, there's no n, there's constant loop bounds and so on, then the problem can be solved optimally using so-called Mirsky's theorem. So we can find the minimal number of data transfers. So I will illustrate this on the example. So we have some complicated program with some data flows. And from this is not really, this view not really obvious how to transfer the data between the executions. But just if we reorder it in as soon as possible scheduling, for instance, we can basically see where we want to transfer the data together, which is just the lines are known in literature as anti-chains. So when we have the anti-chains, we can then just organize multiple values together into messages and transfer those to the target from wherever they have been produced. So this only works if we have non-parametric loop structures. If we have parametric loop structures, we need to do something else. We need to find some integer linear program which actually would find some solution which minimizes the number of messages we want to transfer. I don't go into details in here, but we just modify a bit the algorithm that's also used by Poly for scheduling instructions when to execute then, and instead of instructions we're using messages. So as an example, we have this loop structure before with two statements, and what we can, for instance, do is we have the data of A that is used in statement 2, and we can easily see from this one that we can actually chunk all the data of A1 together in one a message and send them all together to statement 2. We cannot include the int k loop because this would override values. We do the same one for statement 2. For statement 2, in this case, it would just, because the values of B are visible outside, transfer all the data to the actually location where they will be finally stored. So what we need to insert then, we have 4 different primitives. So one is send wait. We wait for a buffer to be available that all the that we can start writing into the buffer. So waiting for the previous communication event to have finished. Then we would assemble the message and then issue the send primitive, which would start sending it to the target nodes. About the same, but in reverse, is for the receiving node. We receive wait for that the value is available for reading from the communication buffer. Read then from the communication buffer and then issue the next receive, so that the sending node could already start sending the data. We have something more because while we are not in such loop structure, we need to what I called a home location. That is, while we're not in the loop structure, the data of variable for array A, for instance, must be stored somewhere. This is a home location which can be supplied by the user. Similar, when we at the end of the scope, we need to write back the data to be available for the next execution of a loop structure. So if we add this to the program, it would look like this. So we have the same sample program as before, and we have 2 communication buffers here, abbreviated to combuf A and combuf B. There are the primitives added when they need to be 1, and there's a special epilogue at the end which would write back the actually data from the combuf into the field of B. So what we did not at this point is add a distribution. So at this point, it was independent on the actual distribution. Where do I store the data? Where do I execute the statements? It's not fixed, so we can think of maybe that every statement is executed on its own private node. But once we add a distribution, we can actually now form where to where we need to send the data. So modified like this, the program looks like this. So this depends on the induction variable counter, I and j. So depending on that value is, we know it's the last, when we arrive there, it's the last message or value written in the communication buffer. We can start sending the communication buffer and so on. So this looks like complicated. So during my PhD, I spent quite some time writing such code, and what's a big relief to actually have this code generated and not have write manually. So in another word, so for the assembly of the message, we need to pick an order, how to the order in which we write the values into the message. So there's an optimal solution of them, which counts the number of indices, would result in expressions, so-called Ehart quasi-polynomials, which can get quite complicated for all of my problems, but it was actually enough to have square buffers. For square buffers, I just take the square bounding box of it, which, if the buffer itself is not a square, would waste some data in the actual message, but for all my problems, this was just the perfect one, and I could get around the more complicated evaluation expressions. So now to the actual implementation. I used multiple components. I modified the Clang front end somewhat for the middle one and the back end using LLVM, and Poly for the actually code generation to get from a scope description to the IR code to be generated. And there's Molly itself consists of multiple components, which I'm going into. So first, what I added to the C++ language, it's a new header, molly.h, and the main content of it, it's a variadic template, which is an array. So it's variadic. We can have an arbitrary number of dimensions. And it has the operator, subscript operator overloaded, so we can use it just naturally in the code. The array elements are in contrast to normal array declarations. It does not allow getting the next element by just increasing a pointer value. This would be disallowed, so you can treat array elements as separate allocations. So then we have a mean to define on which node do you want to store the elements. They are so-called, what I called the home locations before. And this one takes the x and y, x is for a two-dimensional array, and says it's, I want it on store on the node with the coordinates floor something, and a local component to define to define the order of the elements within the same node. So you can see once you can have memory layer transformation just as a subset of distributed memory computation. We just modify the local parts. We can exchange x, y, and z. We can change the order within the same node as well. And then we have for the verb distribution, we also have some pragma where one can define for a specific iteration on what node I want to execute this node on. So this gives me a lot of control about what to give, and the communication part itself is handled by Molly. So this is an example program, how it's looked like. So we have a globally defined array A, which is distributed according to the distribution over there. I have some functions which produces, F serves as a consumer, as a producer, generator, G as a consumer, and the pure annotation says that it's valid to execute on whatever node it is. Otherwise, it would not try to touch it at all and just execute it on all the nodes. So the actually output that client passes to LLVM looks like this. This is already sanitized, so it's a bit small, so I go through all of it individually. First, we have some information about the runtime. This arguably whether it's necessary, but the information I need, for instance, depending on what backend end uses, I have different representation on what a node coordinate is. If you have MPI, for instance, you have a so-called rank, which has no internal structure. If you're using BlueJean Cube, so there are BlueJean Cube, this was my primate machine, you have an array of 5 coordinates, which for each coordinate says where it is, a node is located within the logical architecture of that machine. So for the source, for the array itself, we have, it's declared as a global array. So we have some global thing generated by Clang as usual, but it's also generating some metadata about it. For instance, the array itself, it has this constructor. The constructor does something, and it will later locate malloc the storage required on this local node later. Also have some metadata applied to it, which gives it but the information about which part is the local one, depending on what node we are. We have a separate allocation called Molly fields. This is because the initialization does not need to be in the same translation unit, but other ones may need access the same array as well. So here we have some duplicate information, the information about the home location, the data distribution is repeated here. Actually, I could not make my mind up which approach would be better, so I chose both. So for the array access itself, looks like this. After some unlining, there would be this LLVM intrinsic, LLVM.molly.ptr, which receives the coordinates, in this case in J, in both of them, and return a pointer. With this pointer, I can either load or store value from it, and this was later in the optimizer convert it to a read or write to the communication buffer. So this is an example for one store and from one load. So for the verb distribution, I have some similar thing. You can't, in LLVM, can't annotate types with information, so this is why I had this molly.fields, but you can annotate instructions with something. And for each instruction, I can annotate it with a named MD node about where it should be actually executed, and the molly optimizer would take this into account when possible. So that's one time, the control flow between the molly one time and the rest of those would be like this. So we have some static initializer with what's called the local init, allocates the local part that we need for each of the nodes. Then the main would be called, and actually because at least for MPI requires the argc and argv, I need to pass this information somewhere. So this main itself is wrapped, replaced by some initialization of the runtime and invocation of the mbMPI in it. So this web main would also call the initializer. So we have, it knows statically all the communication buffers and their sizes that I need, and would initialize them, including this MPI persistence communication, MPI send init, MPI receive init. So, and then the main would be executed, which I'll skip for the moment because afterwards it just would do the same thing in reverse, release all the communication buffers, call MPI finalize, and finally return to libc. The program itself would ask the runtime what node actually are we running on, and depending on what node it is, it would then issue the primitives that I presented before, which would then be backed in case of MPI to either MPI wait or MPI start for the MPI persistent communication. So this is how Molly is structured internally. We get some normalization passes in front of it. So the inliner, actually, it's important because the variadic template consists of lots of small functions, and we need at the end that the built-ins or intrinsics land in the place where they're needed. There's some other conditionalization, especially for the loops, required by Poly, and then Molly starts looking for fields. Which are the fields which are in the program for like MD node and so on. So then it's passed to Poly. Poly would look for what the loop structures is, and extract us the information about the loop structure, the scope information that we want to modify in this particular representation. So this information, if we would not run with Poly, with Molly, Poly would just continue to analyze this, get the dependencies, and generate code of it. In case of Molly, this process is intercepted, and we analyze what's the data flow, what's the communication patterns we need to be inserted, etc., etc. And only when these information have all provided and the scope description has been modified, it is given back to Poly. So Poly can generate code for it for the generated for the modified scope description, which depends this time on the node it's executed on. Poly will generate the codes, we do some wrapping I described before, and pass the rest to the remaining lists of LLVM path optimizers. So for close-up, for an example, for the initialization, so in the program, we would, for instance, declare an array. In the molly.h, it says, oh, there's a constructor. It's unconditionally inline. That's what the attribute says there. And it has Clang built in, saying this is the initialization of the field. Clang would then translate this built-in to LLVM intrinsic. So in this case, LLVM intrinsic is called molly field.init. And Molly would look at this field intrinsic and determine what's the local part. What's the size of the local allocation for this field, for this node only, to have a distributed array over there. So this would, in LLVM, then translated again to a call to the Molly runtime, which is called molly local init, which has an argument, what's the number of elements it has. Molly IT would then do a callback back to the function called in molly.h to actually call, we cannot just do malloc, it could be a custom constructor, and this needs to be called, and this is then in the template generated code of molly.h. So relatively complicated structure. So this is example code I actually used for my PhD thesis, which is the Lattice Quantum Chromodynamics example I had in the very beginning. So there are two fields with relatively complicated conditions where I want to distribute it. Unfortunately, it's the easiest way at the moment to define how to distribute it. I envisioned something simpler to type in, but that's where I got stuck with. So on the performance is at the end said it's a BlueJean Cube system, the one in Jülich. And what I got is up to, this is mega loops, mega lattice updates per sites, mega lattice updates per iteration, million lattice updates. And what I got, at least with the no communication switched off, is up to 55% of the theoretically machine peak limit. So this is when you execute FMAs in a row. This is not entirely true because the algorithm you don't only have FMA instructions. So what you actually would get is maximum 78% of the theoretical peak. But it's a lie because it's the one that I optimized manually. So I did a lot of effort, put a lot of effort on the left side on it, like IBM OpenMP implementation is too small, roll out my own. And this kind of MPI is too slow implementation of IBM. Do it using the system programming interface, programming directly on the hardware. So when I do it in Molly, I don't get that optimal code. You see the scale is different. It's about only 1/20th of the hand-optimized code, which is not the encouraging, but doesn't mean this is a failure, because what I wanted to get was in this project for Molly was scaling. I add nodes for more work too much, and the performance per node stays the same. And this is what this graph actually shows. So while the raw performance might not be that good, I will go later into why it's like this, I get some scaling I wished for. So nice constant level of performance depending when I add more nodes to it. So for the discussion, so I compared what I had the manual implementation where I got up to 55% of the peak performance, but with 16,000 lines of of code. So I put quite a lot of effort into my manual implementation. With the Molly one, I got only 25% of the peak, but I only needed about 50 lines of code. And I hit some things in the molly.h library, for instance. The reasons for it, when I looked at the generated code, it's actually not the Molly part that was so awful, but it seems that LLVM was not made for such high-performance scientific computing applications. And especially what I got there was when there was doing a lot of strength reduction, and for that one, using a lot of additional register, which would end up in a lot of spilling. And the whole code consisted nearly only of spilling because the one kernel, one stencil iteration was that large. So what I also had in many implementation, I had vectorization. There was no vectorization in the generated codes. And I had cared for prefetching, which is also not generated in the generated code. So lots of different reasons. But what my vision was in the beginning is not particularly this only application, but I thought about if we do some memory layer transformation, and I see distributed computing as the as a more general part for memory layout and transformation, we can do a lot of work done. So, for instance, what I had, you see on the right, if instead of tiling or so, you would apply so-called space filling curves, Z curve or Hilbert curve, which would make that independent on what's actually cache sizes in use and how many levels out of it. We could have something like, you may have seen from the syntax, the arrays must have constant size, known at compile time. This is syntactical requirement. Also kind of for the required for the tiling at the end. And we could, for instance, have some auto-detection of what we can transform. This is kind of a problem because you need to know every single access which is somewhere in the program, but which could be done if we had some, if we are doing link time optimization where the code should actually be available. So I thank you all for the attention. I'm waiting for your questions.
Questions?
So I don't know if anyone in this room remembers transputers, which were originally designed to solve these kind of problems using channels between the cores.
With what?
Using channels between the cores, so you had low latency channels between cores. Unfortunately, anyone who works in this kind of problem domain suffers from the high latencies we have with sort of modern CPUs with communications. So you mentioned you hand tweaked on your hand tweaked version. How did you manage the communication between the cores?
Between the cores. So as I said, the MPI, what I'm using at the beginning, so start the high-level IPA had some overhead problems. So I was going back to the direct programming of the hardware. So in this case, the BlueJean Cube has some, it's called some messaging unit, which is organized in a FIFO buffer. So they have some data structure in memory which the hardware would read, and where you would add jobs to a queue, including what's the target and the memory address from the target one. So this is kind of direct memory access. This would work without participation of the, let's say, invisible in participation on the receiving side. So it would just appear in the memory on the other side at the end. So I organized it like the pikMPI. I set up all the these queues at the beginning, because I know this one I need always transfer to the right neighbor, the left neighbor, up neighbor, and so on. And every iteration I set up the FIFO queues again to start their job working, and then wait, do some asynchronous computation with the work we do not need the data on the receiving side, and then wait for it. So in the ideal case, and I managed to do this with this mbMPI, I could hide completely the communication, the latency of the communication, by doing the computation of the body part, which does not require the data one. So I tried the same with mbMPI, but it does not work as efficiently.
Yeah, it seems the MPI calls are going to be quite a high overhead to any kind of message communication compared with using hardware directly. Same with the SPUs on the PlayStation, for example.
For MPI, for instance, there's some tag associated, and the implementation must first ask, hello, Node, do you know this tag? Do you know where I need to put the data on? Where I need to put this receiving data? And with SPI, direct programming, you don't have this problem. So I think it's because why it's so much more efficient.
Would it be possible to do this on sort of regular hardware instead of?
So the BlueJean Cube architecture is relatively special. So if you have regular hardware like InfiniBand and so on, you have get the data to transfer to on this InfiniBand card first, and from there on you need to move it to main memory and so on. So it would not work with would only work with a lot more overhead.
Yeah, so we could hack the NIC on a regular PC and kick DMA transfers, and that's probably beyond the scope of this discussion.
There's something in NVIDIA they called something, invented something direct GPU, because they saw if you have some architecture and you want to GPUs, you have to, it would receive on the InfiniBand NIC, go to main memory into a different section that is of main memory that is associated with the memory for the GPU, and from there it would copy it for the GPU again. So
yes, it's an enormous shame we don't have the equivalent of the original link communications.
Yeah.
Anyway, thank you.
Any more questions? Okay, thanks. The speaker.